hope you to be on the right track. If not so, it's time to change your track. And if you're done with it, then today actually we are going to talk about obviously elasticity. But before that, let me tell you one thing. Your decision is not only affects you, it also affects your family, your society, and everything. That's why you have to take your decisions accordingly, so that there will be no harm to them, and you will be also beneficial. Just like if I consider this cube and apply a tangential force along this AB, then it will not affect only the upper surface, it will affect the lower surface, and BC, AD and each of its surface will be affected by this tangential force. So basically we are going to calculate the equivalence of shearing stress, shearing strain, and with the tensile and compressive stress and strain along BD and AC diagonal. So we are starting with shear, means we are going to start with shearing strain. So if I apply a force F, a tangential force F along the surface AB, obviously this thing is considered to be a 3D object, and if I take this side, you will be able to only see a 2-dimensional object and not a 3-dimensional. Here I have made this as a 2-dimensional object for the calculation to be easier, not the calculation to be easier, so that it will be clear for you to understand. So now I am applying a force F along AB. Obviously the AB plane will be a little bit shifted, and as the CD plane is fixed to the lower surface, means its lower surface is fixed to some plane or some ground, and I am applying AB. I am applying a force along AB, which is a free side, means it can slide. So now A will shift to A dash, B will shift to B dash. The plane shifted by this much angle, theta, and we know that this theta is our shearing strain. A little bit okay, this is the shift. Now we have to calculate we know that shearing strain here will be A dash by AD, obviously, and let us consider this cube to be having length L. Then the shearing strain will be this small l by capital L, which is equals to theta, and L by L is actually sin theta. We know that, tan theta, but as the angle is really very small, tan theta will be equals to theta. Agree? Then we have to calculate the tensile strain along dB dash, which is this one. This is dB dash. Initially the diagonal was dB, and then it shifted to dB dash. And if I draw a perpendicular from BD on to dB dash and take this point to be N, suppose, then this NB dash is the increase in length of the diagonal. And similarly in case of AC, if I draw the diagonal and put a perpendicular from CA dash onto AC and name this point as M, then I can see that the compression of this diagonal is AM, means the length of the diagonal, this diagonal, decreased from AC to A dash C, and this decrease is actually A dash C is AM smaller than AC. Now I hope everything is clear. So basically the length of BD diagonal increased and that of AC diagonal decreased, and it is tensile strain, it is compressive. Obviously you can see here there is a decrease and here there is an increase. So accordingly, as this angle theta is really very small, we can say this triangle to be, here there is a 90 degree and this side to be equal, then it will be an right angle isosceles triangle. So here went the amount of NB dash to calculate the strain, because obviously this is the increase and this AM is the decrease. So we want to calculate what is the amount by which the diagonal has increased or decreased its length. So let this be small l, and if this is a right angle isosceles triangle, then obviously these two angles will be 45 degree, and now NB dash will be equals to BB dash. Here it is making a 45 and 45 degree angle. Hypotenuse is making an angle of 45 degree with NB dash. If the hypotenuse is making an angle with that line, then we'll take the cos component. But if it is in front of the angle, just like this point will be equals to hypotenuse into sin theta. You can also do it according to the sin theta equals to sin theta equals to perpendicular by hypotenuse cos theta, and do all things, but it is a shortcut trick to remember, which my teacher taught me, so I am telling you. So VB dash cos theta. Here cos theta is 1 by root 2, so this will be equal to L by root 2. So now here what is the initial length of the diagonal? Initial length of the diagonal will obviously be, here it is L, then this is equal to L square plus L square under root. Under root L square plus L square will be equal to root 2L. So dB, or we can say that also dN is equals to root 2L, right? So now we have to calculate the strain, the tensile strain, means the change in length by the original length, which is root 2L. So now if I multiply root 2 with root 2, I will get L by 2L, which we know that small l by capital L is equals to theta, which is equals to theta by 2. Here you can see that the tensile stress along tensile strain along dB is half of the shear due to the tangential force, and in a similar manner you can also say that AM will be equals to L root 2, yes, L by root 2, small l by root 2, and here AC is root 2L, AM is L by root 2, then obviously the compressive strain will be equals to small l by root 2 into 1 by root 2L, which will also be equal to theta by root 2, means you can say that the tensile stress and compressive stress along the diagonal are equal and half of that of shear. So what I said, here you can see that the compressive stress along AC is being compressed by some amount and BD is being elongated by some amount, and if I take these increase and decrease and calculate tensile strain and obviously compressive strain, then I will get that both of the strain are equal and equal to the half of the shear, where shear is the obviously shearing strain, you know our shearing strain, theta. Everything clear? So now we are going to talk about the relationship between shearing stress. Here this is strain, but we are going to Find the relationship between shearing stress and that of tensile stress and what is that, compressive stress. So let me erase everything, and obviously we will take the same cube A, B, C, D and see from a perspective of this A, B, C, D face and do the calculation. Take the side of the cube to be capital L and do accordingly. Let me first erase this thing. Let us suppose a tangential force is being applied along AB. Here you can see that CD is fixed, and that's why AB cannot just move. Means if I apply here it is my marker, if I apply a force on this, it is rolling because its lower end is not fixed, but here this is fixed, so it can just go forward. But what is stopping it from going forward? As a force is being applied along AB, it should go forward, but it is not doing so because an opposite force along CD is being applied due to this. You can say that reaction force of this F, and now you can see that F is being acted along this direction and CD is being acted along this direction. It looks something like a torque should be there, means it should rotate. But if I take it this point to be center, let us suppose it to be O, then you have the equal amount of force from one point of equal distance. So now you can say that the perpendicular distance in the force equals to torque. Torque should be applied, but it is not rotating, so an equal amount of negative torque will be applied. Negative torque means an equal amount of opposing torque will be there, so we have to take forces that will just oppose this torque. For this you can see that this let me first assign this as let me tell it to F dash dash. Although these two values are same, but I want to show you that this F is rotating it in this direction, and you can see that this F is along this AD and another is CB, and it is rotating along its opposite direction. This is the force and its reaction is rotating it in this direction and its opposite torque along this direction. Now I can erase the dash, so that we will be sure that these forces are same. So now you can see that there is a force along A, B, C, B. It will have a resultant F root 2 F, and here also a F root 2 force. Why? Because when you know the vector law of addition, here they are making an angle of 90 degree, so the resultant will be equals to a square plus b square plus 2ab cos theta under root. So root over of this thing will be equals to f root 2, as square of f is f square plus 2ff into cos theta, where cos 90 is equals to 0, there it will be equals to root 2f, and obviously the resultant is root 2f. Now here I have the force along the surface. Okay, let me first tell you about the surface. I have this force. You can feel that if this is the thing, the force is being acted along this corner. Okay, so now we have to cut this thing. What I mean by cutting it, this is A, B, C, D. So now a force is being applied along this direction. I am trying to make it slice. It is a 3D object, obviously you can see that. If I slice it something like this, I hope you are able to feel that. Means what I have done is I have nothing looking good to this cubic in shape. Let me search for it. Okay, you can see that this is a box. So basically this is I want to show you along this direction so that it will be clearly visible. So if I slice it something like this, I put the something like blade. Okay, just continue with it. If I put a blade at this angle and take it out from this side, I am putting the blade from this side, it will cut along this direction and come from this side. Then I will have something looking at triangular, a pyramidal in shape, and I can draw it something like this. And this is just showing that this is a 3D. Here this length is L. We know that the side of what this cube is L, and its diagonal will be root 2L. Now the force is being applied along this direction, right? So basically we have this surface and the tangential force along it. So now the tensile stress is there. Here this is equals to force by area. Area will be L into root 2L, which is equals to F by L square. Here L square is obviously the area of surface of the cube, F by A. And now consider this the normal cube, and F force being applied along this AB surface, upper surface, tangentially. So F, and the surface area of obviously the upper surface will also be A. You can see that both of the stress are same. And in a similar manner, you can also take this, means you can slice it along AC also. Similarly, you will get a pyramid, but you will get the same shape, but you will get that side to be different. Means obviously this was, you were slicing it along BD and now you are slicing along AC. It will look the same, but obviously we are now talking about AC. So now obviously this will be L, the diagonal will be AC is root 2L, so the area will be L root 2L, and F is also yes, another thing here, F and yes. So now you can see, if I take this force, its resultant will be this way, and this force will have resultant this way, right? Root 2F. Okay. So now you can easily do the calculations and find that the tensile stress and compressive stress are equal to their shearing stress. And this is for today. We'll talk about another topic in the next video. Thank you.